There's some feel-good music to start off. We've got calculus and we've got a pandemic, so we need some feel-good music on the go. We're going to continue on with our lectures here. We're talking about convergence of series, and we've been looking so far at the integral test. That's where we took some series like sum of an, and we convert that thing into a function f of n, and then we're looking at the convergence of that associated integral f of x. And if that thing converges, then the series itself over here converges. This fellow will converge. And if the f of x diverges, then the sum of an diverges. So we finish that off, and we're going to continue on through a couple other different tests to determine the convergence of these series. So here's our first little idea to move along on our next test. So we've got a new idea, and that new idea is if we know the convergence or divergence of one series, you might imagine this one series being something that's very simple, like remember we introduced a p-series last class. So something very simple whose convergence or divergence that we know right off. If we know that, can we apply it to another series? Another series. Something maybe that's not quite so obvious. We used a very similar approach when we did the comparison theorem for integrals a few weeks back. So we would take an integral that we knew to converge, and then we would compare it to something that's a little bit less obvious, and we'd borrow the convergence or divergence onto that integral. So we're on the same track here. We're just talking about series now. So I'm going to draw you a little picture to get us motivated here. And what I'm going to do is, these are like values of n, n equals 1, 2, 3, and so on. And so we're going to imagine that there is some b sub n and a sub n series. So I'm going to plot a sub n here, maybe something nice and well behaved. Okay, terms are going to 0. Very predictable what's going on. And I'm going to connect those with a line here, just so we can keep an eye on it. Keep it straight. So these are all the terms in a sub n, and we would be summing those up from n equals 1 to infinity. So those are my a sub n's. Now then there's a b sub n as well. And this b sub n, I'm going to make it so that not necessarily right at the start, maybe it's below it right at the start, but eventually, let's say at this point here, b sub n is always bigger than a sub n. Okay, so I'm going to connect that also in a line. So there's my b sub n right here. And so the idea is there's some n value that I can move beyond, and then after that point, your bn is always bigger than your an. Okay, or conversely, your an is always less than your bn. We're going to use that as our setup for the next little theorem. Okay, and so this is called the comparison test. Let's write this in here, comparison test. And I'm just going to state just what I've drawn above there. So if you have positive terms where your an's are less than your bn's, and that idea of moving in, as in my drawing past 3 for this to be true, we would say in generally for all n beyond some value, 3 or 12, whatever it might be. Okay, now here's the statement. If the larger of those two series terms, if bn converges, well, look up in the picture. Our an's are always below it and are positive, and so in some sense are bounded above by bn, and the bn is converging. And so the only kind of option for an is that it must also converge. It must be smaller than bn, and bn is converging. So we would say an also converges. And the other side of the coin, if my an diverges, well, now the bn's are above it in value, they're larger than it, and the sum of all the an terms is going to go to infinity, and so the bn terms similarly will go to infinity, and so the sum of bn diverges. Now what this comparison test allows us to do is to take a simple series like P series, for instance, and we can take their convergence properties and we can compare a related series to these P series and attach on either convergence, if we can get underneath a convergent series, or divergence if we're above a divergent series. And I've mentioned it a couple times already, but we're going to state this this very, very common series to compare to. It's called the P series. Okay, and we've already determined the convergence of this using the integral test. So we've got the sum from n equals 1 to infinity. The form of this series is 1 over n to the power p, like 1 over n squared. 1 over root n will be n to the half. Any power of p. We have the property that it converges when p is bigger than 1 and diverges when p is less than or equal to 1, including 1 there. All right, and so the idea is on this thing, we very often use this in a comparison. All right. All right, so I'm going to give you a pretty prototypical example here of when this might come up, and we'll see how this comparison works. So let's do a little example. Does the sum n minus 1 over n cubed plus n plus 1 converge or diverge? All right, looking right away at that, if I considered possibly doing the integral test on that, I'd have to take the integral of a function x minus 1 over x cubed plus x plus 1, which would be a bit of a nightmare to integrate. I wouldn't want to get involved in that. The bottom doesn't factor, really, so you're not even into partial fractions. So we don't want to do that, and we want to always use the simplest tool in our toolkit. So I'm going to approach this very, very similarly to how we did the comparison theorem for integrals. And what we did there was we said, let's get some intuition behind what we're doing first, get an idea of what happens as we go off to infinity, and then use that intuition to guide whether or not I want to be a sort of underneath a convergent series or above a divergent series. All right, so here's my little intuition step. Let's get intuition. And what we want to do is look at that and kind of think, well, as we go off to infinity, what does it look like in terms of a P series? What is it behaving like? And to do that, we would take the limit as n goes to infinity of those a sub n terms, of that n minus 1 over n cubed plus n plus 1. Now, as we go off to infinity, of course, all the terms except the leading term on the top and bottom get very, very small relative to the leading terms as we go off to infinity. So the upshot is that we kind of lose all these terms, and that this pretty much behaves like n over n cubed, which is 1 over n squared. And I look at that n squared and I say, well, p equals 2, bigger than 1, and so my little P series rule says, okay, here we go. P bigger than 1 converges. So I'm thinking this series, although I haven't proven anything, I'm feeling like it probably converges, because in the long run it's going to basically look like a 1 over n squared series. All right, so what I've learned from that is okay, so expect convergence. All right, so now we get to the actual nuts and bolts of this test. So now we want this expression we have, the a sub n, n minus 1 over n cubed plus n plus 1. Now we're thinking it converges, and so we want to get this bounded below some other bn, and we want that bn to be nice and simple, and we want that thing to converge. So the idea is this is going to be less than something, and we might have one of these kind of chains of inequalities, but eventually we get this thing less than something over here that is convergent. And this is what in general we call the bn. And the convergence property, the thing that we intuited in the first step, the thing that we think is it's going to converge, is the piece of information that tells us we want to be less than this Bn. Okay, so if we expected divergence, if I ended up getting something like p equals a half up above, I'd expect divergence, then I'd flip the sign and I'd want to be greater than something that diverges. Anyway, we expect convergence, so now I actually have to perform this. And so we get back to this process again, very similar to the comparison theorem for integrals, where I take, let's make this step 2, I take my n minus 1 over n cubed plus n plus 1. And I want to start removing terms or changing the expression so that it turns into something simple in this comparison. And so the first thing I'm going to do is deal with that numerator. So if I subtract 1 from n, I end up with an expression that's smaller than if I just left the n there. So I can bound this as less than n over n cubed plus n plus 1. So I've removed that 1. And that statement is definitely true. If the numerator is smaller, the whole expression is smaller. And now there's a few terms in the denominator there. There's a plus 1. I'll deal with that first. So adding 1 to the denominator, this piece right here, that's going to make the expression smaller because I'm making the denominator bigger. And so if I remove it, I get something larger. So I can make this n over n cubed plus n plus 1 is less than n over n cubed plus n. And with a very similar argument, I can say that this is less than n over n cubed. The presence of this n term here is again going to make the denominator larger, and so removing it gives me a bigger expression. So that little chain of inequality ends up with a function 1 over n squared. Note that's the same thing as my intuition, and very often that is the case. Not always, but very often. All right, so now number 2 has identified that my n minus 1 over n cubed plus n plus 1, this term I started with, is definitely less than 1 over n squared. Okay, so I move on to my next step here. Okay, I determine the convergence of the Bn. So I say here very simply, since the sum n equals 1 to infinity 1 over n squared converges. And again, all I need for you to show here is p equals 2 bigger than 1. And that tells me you're using the p-series rule for convergence there. That's all I need to see. And since I've just shown that this an term is less than 1 over n squared, and technically positive, formally required, then I have the final thing, which is the statement from the theorem, and I cite the theorem. So I say, then by the comparison test, then the original an, the sum n minus 1 over n cubed plus n plus 1, converges. All right, so it's below a convergent integral. And so, by the comparison test, it must also converge. So that is the 4-step process to answering one of these questions using the comparison test. It's good to first start up here, get your intuition, figure out what's happening as you go to infinity, figure out if you're expecting the thing to converge or diverge, and that's going to influence the inequality that you set up in 2. And you set that inequality up, and you start looking at terms that might be easily removed from the top and bottom, or other expressions, often cos squared x, sine squared x, you might see those. And then finally, you determine the convergence of the simpler Bn that you've determined. Okay. And then you either borrow the convergence property or the divergence property onto your original a sub n using the comparison test. That's how they all work. That's the basic structure of these. We're going to do another one, very similarly structured, just to get a good feel for this. I'm going to get a new setup. And let's do another little example. All right, so imagine this series does the sum from n equals 1 to infinity of 1 over n squared plus n. Converge or diverge. right, solution. Intuition. I'm looking at the limit as n goes to infinity of this an term, 1 over n squared plus n. And so I know it goes to 0, which is good. It has to. But what I'm looking at is basically this is going to behave like 1 over n squared, because the n term is going to be very, very small relative to the n squared term. Okay, so I'm not formally calculating this limit, it's 0, but what I'm looking for is the leading order of behavior on the top and bottom of this expression. So I get 1 over n squared. I'm thinking, again, it's very similar to the last question, 1 over n squared. I expect convergence, okay, p equals 2 bigger than 1. And so now I move into my inequality. So I take 1 over n squared plus n, and I look at that, and I want to bound it below, okay, so I want to make that less than some other convergent function. And now, really, the thing that's on my radar is this plus n term right here. So I think, does that plus n, its presence, make the expression bigger or smaller? And remember, making the denominator larger makes the expression smaller. So 1 over n squared plus n should be less than 1 over n squared. So we're right at the point here. Now we're basically copying the last question. Okay, so I would go, since the sum of 1 over n squared converges, p equals 2 bigger than 1, and step 4, by the comparison test, also my an, 1 over n squared plus n, converges. So very similar structure. You do a couple of these and you get pretty quick at them. So that was a really easy comparison to make in step 2 there. We get our result. Okay. Try another example. Let's just keep rifling through these. Does the sum from n equal 2 to infinity of n plus 1,000 over the root of n cubed minus the root of n converge or diverge? One little note here, n is equal to 2 at the start. That doesn't make any difference at all for us in terms of the work we do for convergence or divergence. It's just an artifact of the fact that when n equals 1, the denominator will be 0, and so it's undefined there. So we just jump up to 2 to avoid that little problem. But nothing changes in terms of our work. Okay, so again, we're going to first form our intuition. Just kind of hand wave the leading order behavior of the numerator and denominator. So this would be like n plus 1,000. I'm just going to recopy this, n cubed minus root n. And as n gets extremely large, it's going to dominate the 1,000. When n is, say, a trillion, it's far bigger than 1,000. And then similarly, the root n term is much smaller than the root of n cubed term. So this is basically going to behave like an n to the 1 over n to the 3 over 2. And that's reducing down to 1 over n to the half. Now here p equals a half, which is less than 1. So here I expect, for the first time, divergence. Okay. I don't know that for sure. I haven't proven anything, but my intuition is suggesting that this is going to look like a divergent integral. Series, sorry. All right, so from our intuition, we now formally try to prove this inequality. So n plus 1,000 for this thing. And now divergence is saying, okay, the next symbol you need is a greater than, because the expression I want to be larger than some other thing that also diverges. That's my goal. So that's going to dictate this symbol here, and then maybe I'll do a chain of these inequalities down the road, but eventually I'll get to something simple and easy to show that that it diverges, whatever this Bn is equal to. Okay, so that's our goal. Now we got to do it. So let's take this and let's go. N plus 1000 over root n cubed minus root n. All right, is bigger than what? Well, right away that plus 1000 on the top is making the expression larger. So if I remove it, I get something smaller, and that follows the direction of the inequality. So that's good. I can say that. All right. Now, let's look at this minus root n term for a second. If I'm removing the root of n from the denominator, it's making the denominator smaller. And when I make the denominator smaller, I make the whole expression larger. So this thing is larger than if that term in the blue box is not there. So n over root n cubed. All right, and again, I've basically reduced this back down to something that looks very much like my intuition term, 1 over n to the half right there. Okay, because this, when I reduce it, n to the 1 over n to the 3 over 2 is 1 over n to the half. It's the same thing. Not always the case, but very often it's the case. Okay, so now I move through my steps. I say, since the sum n equals 2 to infinity 1 over n to the half diverges by calling upon this p-series rule, so p is a half less than 1. Okay, so and n plus 1000 over the root n cubed minus root n is larger than 1 over n to the half. Then finally we cite our theorem by the comparison test in this case. Also, the trickier sum n plus 1000 over root n cubed minus root n, technically 2 to infinity. This also diverges. Okay, it is larger than a divergent series, and so it must also diverge. Okay, straight from the comparison test. All right, so we've got a couple examples now that have gone through. We've done 2 that converge, we've done 1 that diverges, going through some pretty typical examples. And what I'm going to show you now is another example, and we're going to treat it in the same way, but I'm going to show you a pitfall that can happen when we try to follow the same procedure every time with something that looks like this comparison theorem style question. So I'm going to go, does the series n equals, I'll start with 2 again, just because of that same little denominator issue, n squared minus 1. Does this series 1 over n squared minus 1 converge or diverge? All right, so the solution, again, we do use our intuition. This is basically like a 1 over n squared term. P is 2, bigger than 1. Expect convergence. Okay, very similar to the first 2 I've done, in fact. That's what I'm guessing. And so I might go and try to prove this thing. So I would take my 1 over n squared minus 1, and I'd have to make that less than, because of the convergent expectation, okay, less than something else that converges. And so I'm looking at this thing, and the natural inclination is to say, well, what about 1 over n squared? But it turns out that if I have n squared minus 1 over on this side, and if I remove that minus 1, I don't actually get something larger. So the 1 over n squared minus 1 is actually larger than 1 over n squared. Okay, meaning this inequality is not true, and I can't just blindly go and bound it below 1 over n squared. Okay, so I'm actually going to take this, block the whole thing off, because this is not true. So I'm looking at this and I'm just noticing there's not an easy comparison to make here. It didn't follow naturally like the other ones that were a little bit set up, let's say, to use the comparison test. So our usual chain of inequality here that we've used in the past 3 questions, it kind of fails us here. So what do we do? I don't know. Let's try another one. Okay, let's look at the sum of n squared plus 6n minus 4 over n to the 4th plus 3n cubed minus 2n plus 3. Now again, I look at this and I can basically throw out everything in this series in terms of going to infinity, except the n squared on the top and the n to the 4th on the bottom, those leading order terms. So this is going to look like an n squared over n to the 4th, which is basically like a 1 over n squared. So I'm thinking it probably converges, all that go ahead. But then you take that expression, this n squared plus 6n minus 4 over n to the 4th plus 3n cubed minus 2n plus 3, and we'd say less than, and it just turns into a real nightmare to try to deal with all those little terms to try and boil that down to a 1 over n squared. It's not going to work, first and foremost, and it's a lot of work even if it would be perfectly set up for this. So at this point I'm just going to say really hard to make a comparison. Yet I still feel like probably it does converge. It's still going to, as you go to infinity, it's still going to be dominated by the n squared over n to the 4th, and it's still going to behave like 1 over n squared, so I'm thinking it probably still converges. But I'm hitting a wall with the comparison test. It's not really doing what I wanted to in a couple of different contexts. Okay, so one little observation I'm going to make, it really is the behavior as n goes to infinity that determines convergence. And so if it's the behavior as n goes to infinity that determines the convergence, then perhaps I can create a slightly different test that will skirt around these issues I just brought up with the last couple of examples here and indicate that maybe I can just look at the limit as I go to infinity and figure out whether or not the series will converge. And that's exactly what we do, and this leads us to a whole new test, and we're going to call it test number 5. Remember, we're numbering through. So right back from the geometric series test to the test for divergence, the integral test number 3, the comparison test number 4, and now we've got the test number 5, which is basically taking the comparison theorem and pushing it off to infinity. And this is called the limit comparison test. Now it doesn't completely supplant the comparison test. The comparison test has its own use in a couple specific series, but it works well in some other contexts. Okay, so the limit comparison test. Let's start this off by considering 2 series, and I'll generically call them summation of an and summation of bn. If the limit as n goes to infinity of an over bn is equal to some constant c, provided c is bigger than 0, so some constant, not infinity, not 0, but a number, c, okay, a non-zero number, then the statement of the theorem is basically an and bn are going to do the same thing. And so said formally, then the sum of an and the sum of bn converge, or the sum of an and the sum of bn diverge. So they behave the same if their limit towards infinity of the ratio of the terms an over bn gives you a constant, a non-zero constant. That is the limit comparison test. Okay, test number 5 in our laundry list of testing approaches. All right, so we're going to do an example here. I'm going to do the sum, n equals 1 to infinity. I'll go n squared plus 6 over n to the 4th minus 2n plus 3. And our usual question, does this converge or diverge? That's our question. All right. Now, the limit comparison test, it involves an an and a bn, two different series, and I only have one series here. Okay, so I'm going to call that thing an. So my an is equal to this n squared plus 6 over n to the 4th minus 2n plus 3. All right, so the million-dollar question here in using this test is, what is the bn? And the answer to that question is bn is something that you invent. So this is where the creativity comes in. You have to come up with the bn, and you want it to do this. You want it to behave in a way that if you're going off to infinity, the limit of the an's matches the bn, so that they would differ only by some constant, let's say, as you go to infinity. Now basically, what I do in practicality is I take the limit as n goes to infinity of the an and say, well, that's basically like a 1 over n squared. And I try that as my bn. So I'm going to make bn basically the limit of the numerator and denominator of an, which is n squared over n to the 4th, or in reduced form, 1 over n squared. Now, having chosen my bn, I'm going to check that the limit as n goes to infinity of the ratio of an over bn does in fact give me a constant. So my an is n squared plus 6 over n to the 4th minus 2n plus 3. And I'm dividing by bn. Okay, so I'm dividing by 1 over n squared. Let's recopy that. Now, if I am dividing by 1 over n squared, I can multiply by the reciprocal of that term, and it's a lot easier to deal with in fractional form. And what happens is every term on the top just gets an extra n squared attached to it, so that gives me an n to the 4th plus 6n squared on the top, n to the 4th minus 2n plus 3. So now we have a limit expression where we have a polynomial in n on the top and 1 on the bottom, and the degree of the top and bottom is the same. It's degree 4, n to the 4th, top and bottom as the leading power. And you probably remember a little limit trick that says if you have a ratio of two polynomials, or a rational function, and the degree of the top and bottom are the same, then the limit as you go to infinity is the ratio of the leading coefficients, which in this case is kind of a 1 over 1. All right, so we can just basically state that that's equal to 1. Or, if you're uncomfortable with that, I can do this. I can say it's the limit as n goes to infinity of n to the 4th, and I'm going to divide the whole thing by the highest power in the numerator and denominator commonly. So it's n to the 4th, so it's n to the 4th over n to the 4th, plus 6n squared over n to the fourth. You got to do it to every term on top and bottom. N to the fourth over n to the fourth minus 2n n to the fourth plus 3 over n to the fourth. And then you say, okay, what happens as n goes to infinity? That goes to 0, that goes to 0, that goes to 0. The other two terms give you basically a 1 over 1, and that's how you get the limit being 1. Either way is fine with me if you use the ratio of the leading coefficients up here, a-okay, or if you formally divide the whole expression by n to the fourth here and get 1, that's a-okay too. Okay. Now this 1 is equal to my c value in the statement of the theorem. So this limit equaling c, I need that to be a number and not 0. So I go down and it's 1. And so clearly this is a number. It's not infinity. And it's not 0. And so that means it satisfies the condition of the limit comparison test. So now I go back and I look at my Bn. I'm thinking, okay, the sum of 1 over n squared. Hopefully that has obvious convergence or divergence properties. And of course it does. All right, so now I say, since the sum of Bn is the sum of 1 over n squared, this converges, our good old P series, P equals 2 bigger than 1. Since that thing converges, then by the limit comparison test, both sum of an and sum of bn have the same property. They both converge or both diverge. And since the bn converges, also the sum of an converges. And an is that term up top there. So we might as well write it all in to wrap it up, i.e. the sum of n squared plus 6 over n to the fourth minus 2n plus 3, that thing converges. So that's it for this first lecture. We've gone over the comparison test. We've seen how that works. You compare to some simpler function. Often it's a p-series. And then we saw that work in a few instances, but sometimes it doesn't work. And when it doesn't work, when the expression gets a bit unwieldy to make that formal comparison, then we can use the next test called a limit comparison test. And that just involves taking a little limit as n goes to infinity of the ratio of the thing that you are given, and then something that you come up with. Often, again, it's a p-series. And you look at that ratio and you try to show that ratio as a number. And if you can do that, then you can show that they both have the same convergence properties. An and Bn both converge, they both diverge. Okay, so in this case, because Bn obviously converges, and since An and Bn have a ratio limit of 1, then we can borrow that convergence onto An and make our final statement here. So our sum n squared plus 6 over n to the fourth minus 2n plus 3 converges. All right, so we'll keep on this on the next lecture.